In this section, we're going to look at a method of integration called trigonometric substitution. And to solve integrals containing expressions such as the square root of a squared minus x squared, the square root of x squared plus a squared, and the square root of x squared minus a squared, we can sometimes make the following substitution and solve the integral. So for the square root of a squared minus x squared, if I let x equal a times sine theta, where the theta is understood to be between minus pi over 2 and pi over 2, this is equivalent to making the regular substitution theta equals sine inverse x over a. And in this case, the square root of a squared minus x squared becomes a times the square root of 1 minus sine squared theta. And of course, 1 minus sine squared theta is equal to cosine squared theta. So that square root of a squared minus x squared just becomes a times the square root of cosine squared theta. And because theta is in the appropriate interval, the square root of cosine squared theta is just cosine theta. And we can replace this troublesome square root by a times cosine of theta. And the other appropriate substitutions are shown here. For the square root of a squared plus x squared, we let x equal a times tangent of theta, and then we rely on the identity 1 plus tangent squared of theta equals secant squared of theta to eliminate the square root sign. And for the square root of x squared minus a squared, we can use x equals a times secant of theta, and then because secant squared of theta minus 1 is tangent squared of theta, we can eliminate the square root sign from the integral. These calculations are much easier if you use the substitution in reverse. You replace the x by a times sine theta as opposed to using your regular substitution, theta equals sine inverse x over a. Let's look at an example. So let's start with integrals involving the square root of a squared minus x squared. And I show one below, which you could conceivably solve using a regular substitution, u equals 4 minus x squared, but for the purposes of demonstration here, we're going to use this as an example of how we might use trigonometric substitution. So here we have something of the form the square root of a squared minus x squared, where the a is 2, and the recommended substitution is to let x equal 2 times sine of theta. Now this simplifies the square root. The square root of 4 minus x squared becomes the square root of 4 minus 4 times sine squared theta. And pulling out that 4, we get the square root of 4 is 2. And that's 2 times the square root of 1 minus sine squared theta, which is 2 times the square root of cosine squared theta. And because our theta is in the interval from minus pi over 2 to pi over 2, the square root of cosine squared theta is cosine of theta. So we can replace the square root of 4 minus x squared with 2 times cosine theta, and we can replace the x cubed with 2 times sine theta cubed. Now the dx changes. The dx becomes more complicated here. Because x equals a times sine theta, dx d theta is a times cosine theta. So we must replace the dx by 2 times cosine theta d theta. So making all of these changes, we get that our integral is the integral of x cubed, which is 8 times sine cubed theta, times dx, which is 2 times cosine theta d theta, divided by the square root of 4 minus x squared, which is now much simpler. It's 2 times cosine theta. Now we can cancel the 2 times cosine theta, and we get 8 times the integral of sine cubed theta. It's an odd power of sine, so we can use the substitution u equals cosine theta here. We split away a sine, and we split it into sine squared theta times sine theta d theta. And now we replace the sine squared theta by 1 minus cosine squared theta, and make our substitution. Let w equals cosine theta. This is a regular substitution. We have dw equals minus sine theta d theta, and our integral, which is 8 times the integral of 1 minus cosine squared theta times sine theta d theta, is now minus 8 times the integral of 1 minus w squared dw, which, when I take away that minus, becomes 8 times the integral of w squared minus 1 dw. And that's 8w cubed over 3 minus 8w plus c, and replacing our w by cosine of theta, we get that our integral is 8 times cosine theta cubed over 3 minus 8 times cosine theta. Now we must replace our theta by x's, because our original integral was given in terms of the variable x, so it's polite and useful to change our answer back to that format. So theta, our substitution was x equals 2 times sine theta, and it was equivalent to the substitution theta equals sine inverse x over 2, because we chose the angles appropriately. And therefore we can replace theta in our answer by sine inverse x over 2. So now our answer is 8 times cosine sine inverse x over 2 cubed over 3 minus 8 times cosine sine inverse x over 2 plus c. Now these are rather complicated looking functions, but you might remember from a couple of lectures back that we were able to convert these functions to nicer functions in x using right-angled triangles. So let's try to find some nice expression in x for cosine sine inverse x over 2. And remember, the trick was to draw a right-angled triangle where the sine of your angle theta was x over 2, and then figure out what cosine of that angle was. So letting theta be equal to sine inverse x over 2, we have sine of theta has to be x over 2. That would mean that the opposite over the hypotenuse is equal to x over 2. So the simplest triangle to construct is one with the opposite side having length x and the hypotenuse having length 2. And then the length of the third side is determined completely by Pythagoras' theorem. It has to be equal to the square root of 4 minus x squared. And now we can figure out what cosine of theta is. So cosine of theta, which is sine inverse x over 2, is the adjacent over the hypotenuse here, which is the square root of 4 minus x squared over 2. Therefore, we have our integral is equal to 8 times the square root of 4 minus x squared over 2 cubed over 3 minus 8 times the square root of 4 minus x squared over 2 plus a constant. And then when we tidy it up, it looks like this expression on the right-hand side. Let's try another example. In this case, we have the square root of 9 minus x squared, and 9, of course, is equal to 3 squared. So here the a equals 3, and the recommended substitution is to replace x by 3 times sine theta. When I do this, dx becomes 3 times cosine theta, because dx d theta is 3 times cosine theta. And the square root of 9 minus x squared becomes the square root of 9 minus 9 times sine squared theta, which is 3 times the square root of 1 minus sine squared theta, which is 3 times cosine theta. Replacing everything appropriately, we get our integral is the integral of dx, which is 3 times cosine theta d theta, divided by x squared, which is 9 sine squared theta, times the square root of 9 minus x squared, which is 3 times cosine theta. And now we can cancel the 3 times cosine theta, and we're looking at the integral of 1 over 9 times 1 over sine squared theta. Now 1 over sine squared theta is cosecant squared, and if you check out formulas on a formula sheet, or if you just check the derivative of cotangent of theta, we find that the antiderivative of cosecant squared is minus cotangent of theta. And remember, the cotangent is cosine over sine. Our integral becomes minus cotangent of theta over 9 plus a constant, which is minus cotangent of sine inverse x over 3 over 9 plus a constant. We would like to get a simpler expression in x's, and again we construct our triangle where theta is an angle with sine value x over 3. So the easiest such triangle to construct is to have the opposite side to theta of length x and the hypotenuse of length 3. And that gives us the length of the adjacent is the square root of 9 minus x squared. So from this triangle, we can calculate the cotangent of theta, which is the cotangent of sine inverse x over 3, and the cotangent is the adjacent over the opposite, and that is equal to the square root of 9 minus x squared over x in this case. So finally we have a nice expression for our integral. It's minus the square root of 9 minus x squared over 9x plus c. Now this calculation was much shorter than the previous calculation. You can see sometimes the calculations involve quite hefty trigonometric integrals, and sometimes they're much shorter. You can also use this method to derive something you already know, that the integral of 1 over the square root of a squared minus x squared dx is sine inverse x over a plus c. And that's something you could derive using a substitution and your formula for the derivative of sine inverse.